Dear colleagues, I'm glad to see all of you. Now we today have last seminars in this semester before starting the terms of vacations. And let me introduce our speaker today is a professor of Tallinn University of Technology, Jaan Janno. Sorry maybe for my pronounce. So his field of research related to the inverse problem is generated with boundary or initial boundary value problem. Let me remind that it's necessary not find only solution, but it's necessary to find some additional information in this initial boundary value problem related with source, coefficient, and so on. And now is maybe I'm correctly the last 10 years, Jan working also is a fractional derivative in the inverse boundary value problem. So it's very new and interesting investigation and research. So now I hope Jan introduced some inverse problem, and today's talk on some inverse problems that use nonlocality of fractional derivatives. So please, Jan.
Thank you very much. Thank you for inviting me to speak in your seminar. And I know very well the works of Natalia Vassiljeva, also Nicola Krasnochok, the field of differential equations, and also in these fractional differential equations. And equations with fractional derivatives have become very popular in last decades among mathematicians. I think that one reason could be that this mathematics is going to more and more areas of human life and science, and from the classical field of physics, this has gone to biology, social sciences, different engineering sciences, and so on. And it is clear that the classical models with integer order derivatives do not work very well in all such cases, and it's necessary to modify them. And one option is to introduce the fractional order derivatives, and order of derivative that brings some additional degree of freedom to those models, and then it's possible better to adjust these models with different particular situations. And also inverse problems in this context are very important because usually in those equations and models, parameters are unknown and they have to be identified somehow using some additional information which is gathered from measurements of the state variables. And what I have noticed, this is my personal opinion, that there are mainly two general approaches to such type of inverse problems. One approach is that people try to adjust or generalize results or methods which have been obtained already before for equations with and the inverse problems for equations with integer order derivatives to the fractional case. And this is quite prevailing approach. There are different new results regarding Karleman estimates which can be applied to fractional cases also, and also this popular approach of Volterra equations which uses fixed point theorems and so on, and also maybe this maximum principle, which is quite useful technique in some inverse problems also. But another approach is such that which uses specific properties for those fractional equations, and namely the fractional derivative which is involved here with respect to cup order derivative, for instance, is is non-local, and this is something which is essentially different from the integer one, and to use specifically the non-local properties of those derivatives in the equations, which open some new possibilities to pose and analyze inverse problems. And I would like to speak about some such options now. Let's start from this direct problem. Do you see my slide?
Yes, it's in.
And this is the direct problem number 1 here, which contains fractional diffusion equation with Laplacian source term capital F, and also there are initial and boundary conditions added. We consider this equation in some n-dimensional bounded domain. Omega d omega is the boundary of that domain, and fractional derivative dt alpha is here. And firstly, I consider two cases where this dt alpha is a usual first order derivative here, or the derivative of the Caputo type between 0 and 1. This is the second possible case. And in the second case, derivative, as you see, is non-local. This involves the values of w before t, from 0 to t, also here. And now let's speak first a little bit formally about Fourier method applied to this problem. Let us introduce the Dirichlet eigenvalues of minus kappa Laplacian, and V1, V2 are the corresponding eigenfunctions here. And then the notation for any function which is a linear to omega set, I use subscript m to denote the Fourier coefficient of that function, which is namely the scalar product of Vm in L2 space. Further on, I generalize this also a little bit. Now the corresponding family of direct problems it is possible to obtain in Fourier domain, and this is for the Fourier coefficients of the state function u, the direct problem. And the ordinary differential equations with fractional derivatives here with initial conditions, and the solutions are also well known. The formal form of the solution is here, which involves Mittag-Leffler functions. And now let's consider two cases separately. Firstly, the case when we have usual first-order derivative of the order 1 here. Then this Mittag-Leffler function, which occurs in this formula, is simply the exponential function with decaying argument here. This means that here in the second integral, which involves this f, coefficient of source, this kernel is exponentially decaying there. In contrast, when we have the fractional case, then this kernel has power type asymptotics at infinity. This means that we have here such a slow memory or long memory here in this integral of in memory of this source. And this means that this is something which is the feature of this non-local derivative actually. And even more, if I go on, and more detailed asymptotic expansion here, which I have written, is as follows. So principally we can extract the first or the second order and so on. And this is some very rich formula here. This E alpha beta minus d at infinity. And this is useful in some inverse problems also. And this is inverse problem. And this, of course, is related to the fractional derivatives, namely. For this usual derivative, we have no such expression. Before I go to inverse problem, let's formulate some result for direct problem that I also need a little bit. Firstly, I introduce such spaces X gamma, which is related to eigenvalues, and actually they are also the domains of that fractional Laplacian of the order gamma, such a way. And now let's go on to consider also the Fourier coefficient of distributions. And let X minus gamma be the dual space of X gamma, and then I define the Fourier coefficient of any element Z as a pairing between Z and eigenfunction. Eigenfunction Vm belongs to all that space is X gamma, where gamma is positive. And so it is possible to do it so. And it's possible also to generalize here the widened domain of this Laplacian by such a way, which are written here. And it's possible now to consider the equation so that the function that we are searching for has such a distribution values in T. I want to do it because further on I consider also such problems where we have Dirac delta distribution point sources there. So this distribution formulation is also necessary. So such existence regularity results of the solution of direct problem I have written here. We assume that alpha is between 0 and 1. So principally now I forget this case alpha is equal to 1. I go on with the fractional case only. And fxt has the form of separated variables here, this source term. This is the main form of the source term that I will use in inverse problems also later on. And we assume that this f belongs to X gamma for some gamma, and the T-dependent factor is in LP space, p is greater than 1 of alpha, and the initial condition phi is in such space. And then the direct problem has a unique solution in the following space. HPS is a special spot potential space here, and also C, this is continuous from 0 to capital T. This is important because I want to use traces at capital T here for inverse problems. And this continuity condition is somehow important, and to use the final data. And this is the theorem for direct problem. And now let's go to inverse problems. So first class of inverse problems that we would like to consider, they are problems with final overdetermination in such form. Utx is psi x. This is the prescribed function, additionally to initial condition and boundary conditions there. And firstly, let's consider such problem that we want to reconstruct function fx in the source. G is a given function. And using this final overdetermination condition. And principally, such type of problems are very well studied, both in the usual diffusion case when we have first order time derivative, and also they have been quite well studied in fractional cases. There are many papers. And those problems are actually quite good problems in this sense that we have here some kind of moderate ill-posedness. This means that this f depends on second order derivatives of psi continuously. Another problem is such that f is known, g is unknown. So we want to reconstruct from this final data the time-dependent factor. And such problems have not quite well studied. Even I do not know the references in case of usual diffusion equation when alpha is 1. There is one paper that I have found. This appeared in 2015. And there they say, the authors say that this problem has not been completely studied in case alpha is equal to 1. But what turns out that in fractional case, this problem is much easier to handle than in the usual diffusion case. And this is thanks to that power type asymptotical formula that I showed before. This is useful here. And what I have to say that principally I now go to the uniqueness of this G reconstruction, uniqueness of this reconstruction. And then I still cannot prove it completely. I still have to assume that nevertheless this unknown G is known in some arbitrarily small neighborhood of capital T, then everything works. And also some words about F. Let's go back to the formulation. I want to reconstruct G, F is given. Of course, we need here certain assumptions about F also. Of course, for instance, if F is 0, then we have no hope to reconstruct G. But what I need here actually even more, that this F is non-generate function. This means that we can find a sequence of indices M1, M2, and so on, that the corresponding Fourier coefficients are not 0. So when there is this...
Jan, sorry, I have some question. If your function f, given function f, for example, vanishes in couple of points, what happens in your situation in this case? If your function f, given function, for example, have a couple of zero on your domain.
0 points. This doesn't give any problems in that situation, because you see this f is given for all x from in this domain omega. So this means that you can always choose some point where f is not 0.
Okay, thank you.
Because we have here product.
Yeah. I understand. But for this reason, appears this question.
So, and can I continue? Okay, and now this theorem. And here is some assumptions that f is non-generate, as I wrote here, and I assume that this LG unknown is an LB space for some p is greater than 1 over alpha. And also, what I had to say in general, that this is a linear inverse problem. This is a linear inverse problem, and then the uniqueness principally means that the 0 data implies 0 solution. This we have to show for the uniqueness. So I assume that the data, this G is 0 in an arbitrary, in some arbitrary small neighborhood of capital T, as it's written here. And if the solution of the direct problem satisfies the 0 conditions, is 0, 0 at the initial point, at 0 at the final point, then the solution G is completely 0. So this is the result. And now,
Jan, sorry, it's very strange because your function G is unknown function. How you can assume G equals 0 almost everywhere if this is unknown function? How possible?
I said you before that I must notice the G from T minus epsilon to T.
Yeah, but you consider situation when F fixed function, G unknown function, yeah?
Yes.
How you can assume exist in some epsilon such that G almost everywhere equals 0 around at the end point? It's very strange.
You have additional information.
You need to look for this function.
Yes.
My understanding.
This G is a priori known.
Yeah, exactly.
From T minus epsilon to T.
Yeah.
So this is measured in some neighborhood of capital T, and then we want to go back.
Yeah, I understand. But if you put, for example, G given function at the end point, it's very strange trick. No, because my understanding, if you know final value unknown function at the end point, this may be enough because you have linear problem. You can No.
I don't understand. What do you mean?
No, look at
GT at final point, but this doesn't mean that you can extend it automatically to some.
Yeah, but
this is not generally not analytic function.
Jan, you put G not at the one point. You put G almost everywhere 0 at the some interval, small interval, but interval.
Yes.
One
additional information, Roman.
This is additional information.
Sorry, if I understand right, so it does not enough information about the function u in the final point to prove the uniqueness G of t. Yes, correctly I understand it. That's why you need additional information about function g for this small interval. With time. So in it's possible you have two additional conditions. Function u in the final point, and you have information.
You can put extra condition on unknown function. It's very strange.
Roma, do you understand that to prove uniqueness?
Yes,
it's not
here
enough.
Is necessary in my proof. It is sufficient to know G in some interval, arbitrarily small interval. This is the point here.
Yes.
Not only exact single point, but in some interval. This means that one must know it in some set which has one positive measure. This is necessary.
Okay, thank you.
Is it okay?
Okay, so sorry, please.
So I want to sketch the proof also, and there we can see why this additional assumption is necessary here also. Not necessary, but sufficient, actually. So if I go back to that solution formula in the Fourier domain, then what happens that some terms here vanish, initial condition vanish, we have not, final condition is 0, and since G is 0 in that subinterval T minus epsilon to T, then we have such relations here, what you see on the screen. Actually, family of relations, sorry. Family of relations for all m, corresponding to all those Fourier coefficients. And now what happens here that further, if using this non-degeneracy condition for f, we can extract the subsequence of those relations where this f, factor f is not 0, so we can divide by this and get this family of relations here, which is written. And now let us notice that integral is from 0 to capital T minus epsilon here. this means that actually the function under the integral has no singularities anymore. Because t minus tau to power alpha minus 1 has singularity in the point tau equal to capital T. But now this singularity is cut away. And so actually we can now use this asymptotic expansion here for that Mittag-Leffler function. We can put it inside and go inside the integral with that one. So the result is now here. This is that formula. And here we have even a stronger singularity, t minus tau alpha n minus 1 plus 1 here. And this here arbitrary lambda principally, which goes to 2 until infinity here on all those relations. But we can do it because actually this singularity here lies outside the domain of integration. Integration is from 0 to capital T minus epsilon. And certainly here is not enough to have only capital T here in this place. So we must have here some interval, some arbitrarily small interval around this capital T where G is 0, because otherwise this substitution doesn't work. That's the point here. So now let's go on with this asymptotic relation here and take it from some n0 here. And at the left-hand side, we have such terms 1 over lambda nj to the power n. And this n is less than n0 plus 1. At the right-hand side, we have such term which goes as lambda 1 over lambda nj to the power n0 plus 1. As such order if lambda is j goes to infinity, because 1 over lambda j approaches 0 here. And here we can make such a simple conclusion that all those factors of 1 over lambda and jn at the left-hand side must be 0. Because otherwise we get the contradiction. The left-hand side has a lower order asymptotics than the right-hand side. So, and now the conclusion is that all those coefficients are 0 here. And this means that we have such family of new relations here for this G. Now I simplify a little bit. I read, 10 minus 1 pi k here. So we have such relations where k is arbitrary integer here. And now let's work with these relations. So in this sketch of proof, for the sake of simplicity, I assume that alpha is irrational. Because if alpha is irrational, then all those factors, 1 over gamma minus alpha k here, they are not 0. If alpha is rational, then we have still some little additional difficulties here because gamma function has poles at negative integers. And this means that this 1 over gamma minus alpha k for some case becomes 0. But nevertheless, it is possible to work also with the case alpha is rational. But for the sake of simplicity, I assume that alpha is irrational. Then those factors are non-zero here, and we get simply pure integral relations for G. So I do the further change of index here. M is k minus 1. And now I factorize here inside the integral. I take the first term 1 over t2 minus 2 to alpha m, another one which contains g and something more here. And still I want to point out that all those functions here except for g maybe are infinitely differentiable inside. And also they do not become 0 anywhere. And now we can make a change of variables under the integral, make such substitution. S equals 1 over tau t minus tau to alpha. And the result is that we get such Hausdorff moment problems here with 0 theta. And it is well known that the solution is 0 here. R is 0. And then if R is 0, then G is 0, and proof is finished. So I want to go to next inverse problem, and maybe you have some questions for this inverse problem still.
What happens if you take, for example, G at the end point as some power exponent function dependent on T capital? It's possible. No, if you assume that G not equals 0, yeah, at the end point, but have some exponent behavior.
Yes, I understand your question that in this case we have always integrable function on that. Maybe this works. I have tried it also, but I have not yet obtained any results. Yes.
Jan, if I understand right, you prove uniqueness in the class of function g of t with compact support, yes? No, it's reformulated with g of t equals 0 for t minus epsilon t. It means the support function g of t belongs from 0 to t minus epsilon, yes?
Yes.
Yeah, so sure. But it's possible to t tends to infinite, consider this problem, or any fixed t?
Yeah, here is impossible.
Capital, what goes to infinity?
T capital only fixed t, yes? It's not, it's impossible to be t capital is infinite, yes?
Go to infinity.
I think that this is how you measure the function at infinity.
No, approximately we assume the solution of uxt.
You mean that we know the limit of this u at infinity then?
Long time behavior.
Yeah.
Actually, this is the same point where the measurement is given, observation capital T here.
Yeah.
And can reconstruct. I have thought about the case when we actually have how about minus infinity here instead of 0. And this may also work somehow.
Thank you.
When we have something starts from the minus infinity, I think so. This may be also possible.
Okay, and I have a question related with direct problem. Is possible the theorem 1, where is you prove solvability in the class HS, but I guess as HSP as how is related with the order of derivative alpha, maybe, or with gamma. You belong to HSP and S.
Oh, yeah.
How is defined? I guess S maybe equals alpha.
Alpha, of course.
Yes.
Yeah.
Sure.
S is alpha, yes.
Alpha, yes, sure.
Yes, you are right. There I have some misprint.
Thank you.
There is some misprint. This must be alpha,
yeah. Yeah, sure. Thank you.
This is alpha, yes.
Thank you very much.
How much I have still time?
Oh, about 30 minutes, I guess.
30 minutes?
Yes, 30 or 40 maybe it's possible. Due to we have some questions and some technical problems that are in the...
You mean that I still have 40 minutes?
Yeah, okay.
Then I will spend much more than 1 hour. Okay, I shortly speak about other problems also in this, which are actually generalizations of that one.
Mm-hmm.
Next, I would like to formulate such problem where we have 2 unknowns of such type there. And in both unknowns, the x-dependent functions are given, and then G1 and G2 are unknown. And here, of course, it is by means of the same single measurement, U capital D psi x, and maybe this works somehow. But we still need here that this f1 and f2 are sufficiently different functions. Because, for instance, if f1 equals f2, then clearly it is not possible to separate g1 and g2. And let us introduce such space here, which looks a little bit complicated. And the pair of functions f1 and f2 belongs to SD. That there's an abbreviation of sufficiently different pairs. That which is written here in general. And roughly speaking, the meaning is that the quotient of Fourier coefficients of f1 and f2 multiplied by eigenvalue to certain power k, which is a whole number, has not finite non-zero limit, then they are sufficiently different. Such concept. And now, next theorem, which states the following, that principally in such a situation it is possible to reconstruct both G1 and G2. And again, only in the case when we have they are known still in t minus epsilon to t. And how to work in this case, main idea is that, again, I go to this relation, what I get from the solution formula of the direct problem in Fourier domain. And now we have two add-ons there. One contains G1, another one G2. And then what? We can again use this asymptotic formula and go inside this integral, because we have here singularities are cut off. And now, thanks to this assumptions that f1 and f2 are sufficiently different, it is principally possible to extract the subsequences, proper subsequences, so that in the first subsequence, the first term here in the left-hand side dominates, in the second one, the second term. In such a way, it is possible to get two relations. So what I want to say in general, that this situation when this f1 and f2 are sufficiently different is quite informative in this sense that we can work with different subsequences here. And the other part of the proof is then exactly the same as in the previous proof, that we can, again, using the substitution to go to this Hausdorff moment problem with zero data, and then to obtain that G1 and G2 both are zero. Now, another corollary of this theorem, what actually I can do here is that to consider the problem when we have such unknowns, G and the point x0 where a point source is located. So this is in such form. This is principally the reconstruction of location and time history of a point source. And here is now the uniqueness theorem for that case. Here we have non-linear inverse problems, so it is formulated in such a way that I suppose that we have two functions, f and f tilde, with corresponding time factors g and g tilde, and the points x and 0 and x0 tilde. And what I forgot to say, that I am able to prove this uniqueness only in one-dimensional case so far. The generalizations to multi-dimensional case look for me quite difficult. I need here certain specific properties of eigenfunctions that I don't know still, but I will speak later on about this situation. And now assumptions of this g and g tilde. And again, the same kind of additional assumption that here I need actually that they both are 0. But so actually we had here, we have such situation that we measure this data utx after the accident in some sense, that both sources are 0 already in the neighborhood of this capital T. And important assumption also that at least one of them, so we can principally assume that G is not completely 0 before that. And let U and U tilde be the solution of direct problem. And if U tilde and U tilde equal to each other at the initial point and final point, and these G's are equal to each other and X0s are also equal to each other, such theorem. And proof uses the previous, namely in such a way that firstly I compute difference of F tilde and F and rewrite this difference in such form. The first term is G tilde with a factor F1x, and then another one of F2x. And both functions are non-generate functions. This is not so difficult to see that Fourier coefficients of this data function, the sequences are actually non-generate, so that we can find arbitrarily large eigenvalues so that they are not 0. And then let's assume now that suppose that x0 is not equal to x0 tilde. And then in the one-dimensional case, I am able to show that F1 and F2 are sufficiently different. This is now the point where I couldn't generalize the result to the multidimensional case. In one-dimensional case, those eigenfunctions are very simple. There are sine functions with some coefficients and so on, and it's not very difficult to prove that they are indeed sufficiently different.
Jan, sorry, what means your notation SD? This is Schwarz space?
This is, let's go back to this definition.
Yeah. What means SD?
It is here.
Yeah. What means SD?
This is the definition of SD. This means, roughly speaking, that the quotient of Fourier coefficients of F1 and F2, which are written here, multiplied by any lambda n to the power k. The k is a whole number in this case, negative or positive integer. This has not finite limit, which is different from 0. So such assumption.
It's not look like is not natural.
What?
No, a priori, you don't know anything about your. Okay, please give me an exact example, if you have, of course, such type function f1 and f2.
They both are in SD.
Yeah.
F1 is Laplacian of F2.
Okay.
Then we have this limit is 1.
Yeah.
Actually, they are equal to 1 because we have here lambda m to the power 1.
Okay. Thank you. I understand your logic.
Is it okay? Yeah. Or they are equal to each other, and so on. So I agree that it's maybe from practical viewpoint, it is not easy to show it, that it works. But actually, if we have this F1 and F2,
Yeah, because this is very specific condition. It's not
but
general.
I wanted to apply it now in the specific situation.
Yeah.
Particular situation when F1 and F2 are theta functions.
Yeah, you prepare your next step connected with delta function, direct function. Clear.
Yes.
Thank you.
And now we have this one-dimensional case when this Fourier coefficients of delta functions are simply sine of something. Sine of something, and another one is sine of another thing. And they are not belong to this pair of functions that belongs to this sufficiently different space. And then now I can apply this Weaver's theorem. And since the final condition in this difference situation that we contain a problem for u tilde minus u is 0, Weaver's theorem implies that both g and g tilde are 0. But what we have assumed also in this theorem, that this g doesn't vanish completely. This means that we come into the contradiction. And this contradiction shows us that this supposition that x0 is not x0 tilde was not right. And actually we have x0 is equal to x0 tilde. And now next is thanks to this result, this difference of sources has such form now, and I can apply theorem 2 and to get that the difference of g is also 0, and this proves this theorem as well. So that's the two inverse problems. Before I go on, maybe you have some additional questions about this part of talk? My problem was here to prove here everything for the multidimensional case also. When we have this delta function, at x0, another one located at x0 tilde, and multidimensional case, and can we show that then this two functions f1 and f2 belong to this ST. That they are sufficiently different. Here I must work with eigen values or eigen functions at certain fixed points, x0 and x tilde actually. So this is what I don't know still. And maybe short because I don't want to be very long with my talk. A little bit about problems with unknown boundary conditions also, which are related to that kind of theory. Here the main point is that if we have multidimensional case, then the observation function is the function of n variables, which is greater than 1. But if we want to reconstruct G, then the unknown is the function of one variable, single variable. And this means that in multidimensional case, the problem is somehow overdetermined. And then I wanted to go over to the case when unknown depends both on t and n-1 space variables also. Then we have, in some sense, balance between this unknown function and this observation function. And such functions occur in boundary conditions. They depend on n-1 variables on certain manifold and also on time t. That's why I considered such inverse problem with unknown boundary conditions. Here I was successful only in the case of cylinder. The capital omega is cylinder of such form. And this small omega is the shape of that basis of this cylinder. And here we have the same differential equation written here, and also initial condition, and boundary condition on the lateral surface is denoted by H here. And boundary conditions on the basis of the cylinder are G0 and G1 correspondingly, and they are in our situation unknown functions. But, however, again, known in T capital T minus epsilon to capital T. So, and here is the uniqueness result for such a situation. And about the proof, again, this is very similar to the proof of that theorem 3, where I considered two unknown source terms. Here the boundary conditions on both sides, both bases, they occur in the solution formula so that the coefficients, they are sufficiently different, and we can again separate somehow subsequences and work with them. And now, in the next part of the talk, I would like to speak about some other type of inverse problems. And here the observation is given on the, not on time value, final time value, but in the neighborhood of final time value, t minus epsilon to t. This is the observation of u, state function. So in previous problems, we had observation at capital T only. Now we have more observations for the state function. And this is a joint research what I did with Natalia Kirash. Natalia is originally from Lviv. She was a student of Mykola Ivanchov, and she defended master thesis in Lviv and came to Tallinn for the PhD study under my supervision, and defended the thesis in 2020. So here is such a problem that first I consider here again Caputo derivative of the order 0 to 1. And this is formulated so that u and its fractional derivative be known in the time interval from capital T minus epsilon to t. And the purpose is to find ut before that t minus epsilon from 0 to on this interval to reconstruct it. And the formulation of such problem seems natural, Because actually this fractional derivative in that interval from z t minus epsilon to t contains information of u before that t minus epsilon. It contains this history of u. And of course, this is again some problem that this is such a problem that has no sense in the case of integer first order derivative, for instance. If we had here first order derivative, then we cannot expect that we can construct this u here. So, and there is this uniqueness result. Principally, we have here again linear problem. This means that to show uniqueness, we must show that zero data implies zero solution. And so here are zero data. U is equal to ut, they are both zero from t minus epsilon to t. And then this implies that u is also zero. And I want to speak about the proof also. What we have assumed that u is zero there from t minus epsilon to t. And this is w11 function. And then I extend it by zero until infinity, this u. And now let's go to another function f, which is the fractional derivative of u. And if u is extended, then principally this f is also extended, because we can extend this fractional derivative also until infinity. And now let's look more closely on this f. Now there is the formula of f, this fractional derivative. This is such an integral here. And since u is zero for t is greater than capital T minus epsilon, then we have such relation here, which is written here. And this holds for t which is greater than t minus epsilon. And here, again, we have such a situation that this singularity is cut off. Singularity which is contained in this t minus 2 to minus alpha. And principally, this t minus 2 to minus alpha becomes now analytic function. And thanks to that one, f is also real analytic. For all real analytic in the domain t minus epsilon to infinity. But now what we have assumed that f is zero. This fractional derivative is zero in that particular subinterval, and since f is a real analytic for all t greater than t minus epsilon, we'll automatically analytic extension get that f is zero for t minus epsilon to infinity. And the conclusion of that fact is that f has finite support. By the assumption that I imposed on u, and also by the extension, u has also bounded support. Now I introduce w, which denotes the first order derivative of u, and w has also bounded support. And now let's go to Laplace transforms. They are entire functions, because they are Laplace transforms of functions that have bounded supports. And now let's compute next a simple Laplace transform relation from that convolution. F equal that convolution, and we get such simple product relation. And now next, let us assume that w is not identically zero. And then principally we can divide this relation by w hat, because W hat may become 0 only in some countable set of zeros, and we have such relation on that the right half plane now. And next, since this F hat and W hat both are entire functions, this left-hand side in this relation is holomorphic on the whole complex plane. Not holomorphic, but meromorphic, excuse. Or can be extended as meromorphic function to the whole complex plane. But the right-hand side is not meromorphic because this has branch points. Branch point at 0 because this alpha is between 0 and 1. And this shows us that we have come to the contradiction. And what was now wrong? It was wrong that we supposed that W is not identically 0. This means that W is a 0 function, actually. And we defined this W as a first-order derivative of U. And there is now the conclusion is that U is constant function. But by the assumption U is 0 on that subinterval, and this means that this constant is 0 and U is 0, and theorem is proved. Such type of result. And if I come back to this formulation here, okay, this can be handled, this can be applied for some other inverse problems, this type of result, and also to some inverse problems. Source identification, and let us now look how this can be done. Now I come back again to this fractional diffusion equation here, which is written in this form. And now the aim is to reconstruct x and t dependent right-hand side. So we have not it anymore in the form of separated variables, but some kind of general such source. But I assume that the source is 0 in some left neighborhood of this capital T. This means again that we consider some situation that occurs after the accident. And on the other hand, let this UXT be measured or given, in other words, in this subinterval for all omega. And the aim is to reconstruct the source for the time history of this source for all x. And here it is interesting that we can work without any conditions. And the initial condition also. And we can even take some subdomain omega of the wider domain where the process is going on and so on. And let's do it so that firstly, this assumption fx t is equal to 0 from t minus epsilon to t simplifies this equation, because for that subdomain of subinterval of t, this right-hand side f at the right-hand side becomes 0, and we have the right-hand side in such form, the equation in such form in this subinterval. Now next, since we know uxt for t minus epsilon to t, we can compute Laplacian also. There. And since Laplacian is known here in this equation, the left-hand side is fractional derivative. Principally, we can compute the fractional derivative also using this Laplacian left-hand side. So now we have both u and its fractional derivative for t minus epsilon to t. And using this inverse problem for a fractional derivative that I showed before, discussed before, we can reconstruct the time history of this state function u before that t for all values of x here. And using this time history, principally we have now this state variable, state function u, where all variables x and t, and then it's possible to compute everything. This fractional derivative and Laplacian and so on, and compute also the right-hand side of the equation, which is the source term that we actually want to find. So that's all. And in this theorem that I proved with Natalia, we did it actually in a more general form. Not to this, not only for this Caputo derivative in the of the order between 0 and 1, but for certain generalized derivatives. And maybe I shortly touch this case also, and this will be the final part of my talk. So first, let's consider the Caputo and Riemann-Liouville fractional derivatives of the order between n minus 1 and n, where n is an integer, and they are defined by such formulas. And if I generalize them, then I simply replace this kernel, which occurs here in this derivative, by means of certain more general function, kt, which may have singularity at 0 points. And then I get such generalized derivatives of Caputo and Riemann-Liouville type. Such type of derivatives have been studied also in some works, for instance, Yuri Luchko, and maybe some other persons. And now I formulate a similar inverse problem for such derivatives. So this is so that we have some integer and some kernel, which is locally integrable in general, and d, bold-faced d, which is either the Caputo derivative or Riemann-Liouville generalized derivative. And let this function u here, function u, and this bold-faced generalized derivative be known in interval capital T minus epsilon to t capital T. And then the purpose is to find this ut from 0 to capital T minus epsilon. And now this is the uniqueness theorem for such case. So most important here maybe these first three assumptions about the kernel. And here I assume that this exponentially bounded kernel at infinity. And then kt is real analytic from 0 to infinity. And the Laplace transform of this k cannot be meromorphically extended to the whole complex plane. And here are also some regularity assumptions for that u. And finally, the statement is that if u and its a generalized derivative is 0 from t minus epsilon on t, then this u is identical 0. So this is the result. And proof is very similar to this particular case. So namely, in this Laplace domain, what we had this basic relation that I analyzed here. Sorry, right point, yes. This is what we had here in the Laplace domain. Here, instead of this 1 over S1 minus alpha, we have this K, Laplace transform of the K. And maybe also something more here, additionally at the right-hand side, which come from the fact that we have not the first order derivative, m maybe arbitrary integer. But nevertheless, we have the same situation that we can transform this relation to such form that left-hand side is meromorphic on a whole complex plane. But on the right-hand side, we have now K hat S, which by the third assumption in this theorem is not meromorphic. So that's all. So I have finished my talk, and thank you for the attention.
Thank you very much, Jan, for so nice, interesting talk and interesting from your approach. So, and do you have some questions, colleagues? Comments? If you have problem with English, I can translate it.
Okay, Natalie, my comment is next. Why you need constant kappa in your equation if you can eliminate this constant by rescaling, simple rescaling? Why this is principle for you?
About what equation?
Jaan, understand me? When you consider your equation, you have constant kappa. Yeah.
Yes.
Why you need this constant if you can by rescaling eliminate this constant? It's principle for you because it's a known constant. Yeah.
I don't know. Maybe indeed. Rescaling actually it means that okay. In general, we have here two constants. One is here before that fractional derivative. We practice another one is this diffusivity, which is here. This is kappa. But I am not completely sure that both can be eliminated by rescaling the time.
No, not only time. You have space and time. No problem. Well, I am not a great specialist in fractional, but my opinion, this constant is not significant and can
maybe
be
yes, maybe yes,
by conjecture.
Right. Maybe yes, you are right. Maybe so, yes.
Of course, if you want to consider case when diffusivity is some function, yeah, in this case, not clear.
Yes,
but if you consider only constant diffusivity, no problem, maybe. Okay, thank you.
Thank you. Yet questions? Comments? So I have question yet. Jan, when you consider problem wave f of tx depends of f1 and f2, if I understand right, the condition SD means that the function f2 is more smoother than function f1, yes?
No, this is the
SD condition for f1 and f2.
No.
So this doesn't mean that. No.
Oh yes, yes.
This is formulated so that it is not.
It means f1 is more smoother than f2. Yes or no?
No, Natalie.
It is
right.
not possible.
F1m and f2m is a Fourier coefficient. Yes.
Yeah.
And if function f1 and f2 is more smoother, their Fourier coefficient is decay in the infinite. Yes. No, due to we have the is integrated by parts. But
yes, if they don't belong to ST, then such cases may occur. That if they are smoother, for instance, if
yes,
F1
F1 is F and F2 is Laplace of F. Yes, it means the function f is more smoother than f2. f1 is more smoother than f2. So due is.
But they may, if k is 0, then the smoothness is the same actually, because k may be 0 also here.
Yes, but it means if the k is not 0, it's.
Then the S1 is yes, maybe one is smoother than another one.
Of course, my opinion, this is structural condition must be eliminated because it's not natural.
No, it's related with
Structural condition, yes. This is limit condition, of course.
Yes.
Because it describes the behavior of function f1 and f2, but in the term of the Fourier coefficients.
It is possible just to give some simple examples. So this relation doesn't know, this means that this limit exists. So as I said, one is Laplacian of another one, or one is constant times another one, and so on. But yes, in general form, I have an exact example only in this case when we have delta functions there with concentrated in different points in one-dimensional case, when this ST condition holds, that we have not such limit.
Thank you. And also I'm interested in how this result fits the case of alpha equals 1. So I keep in mind, or maybe correctly saying it's possible to you apply your technique for if we consider the problem with alpha equals 1 and prove uniqueness.
No. This is completely different case because I use here this power type asymptotics, which is valid only when we have
Metach-Leclerc function and in
alpha
exponential.
In the case of non-integer alpha. If we have alpha is integer 1 or 2 and so on, we have here some exponential decay of. Yes.
Okay.
And then I cannot, because I need those different levels of asymptotics to get enough limit relations to cover this different situations to get this Hausdorff problem. The Hausdorff problem finally. So this is the main difference. Now, how to work in the case of integer alpha equal 1, actually I don't know, because this is, in my opinion, has not been studied even. This open case. Maybe the uniqueness doesn't hold at all.
Thank you. So, yet questions, comments? So, thank you very much, Jan, again. So, thank you very much. We have.
I have wasted a lot of your time. How is the situation there in your?
In Ukraine, but maybe it's possible Roman say about it. I'm in Italy now, so the situation here is, of course, it's good, but as for Ukrainian situation, maybe not
Italy,
so good due to it.
Vladimir Fedorovich.
Что? Sorry?
What was question, maybe? I don't know.
I don't understand. Fractional derivative, not for me.
Okay.
I know, don't know apparatus of fractional derivatives. No.
Techniques. Okay, so.
In fact, this is integral equation.
Yes, integral differential equations. Yes, sure.
Yeah. Last decade, very smart guys can start this fractional derivative. But before many years ago, this very famous integral equation. Okay.